This is AP Calculus BC, and in this video I'm going to talk about the last two sections in this unit. The first one is evaluating definite integrals by substitution, and then the last section in the unit is 5.10, which is really mostly about functions defined by integrals. So in this section, evaluating definite integrals by substitution, you're going to see that this is really just a little bit of an extension of what we did previously in this unit when we did indefinite integrals by substitution. So I've got a worked out example for you here that I want to show you first, and then I'm just going to go through a couple of these and then have you try a couple of them, and you'll find that this is really almost the same thing as what we were doing before with just one minor tweak. So it says solve this integral from 0 to pi over 3 tangent x secant squared x dx by substitution. Okay, so pretty obvious substitution here. You can see u is tangent x, the du is secant squared x dx. We also could have said u was secant x and used du to be secant x tangent x. It doesn't really matter. The main idea is that not only do we have to do that substitution, and you can see everything is there, but we also have to account for the fact that when we do our substitution, we're going to turn all of this stuff into an expression in terms of u. Well, these values that I have right here as limits of integration, those are x values. So I'm going to have to convert those over to u values. And you can see it's pretty easy to do because we've got this relationship here. U is equal to the tangent of x. So any x value I have, to find the u value, just take the tangent of it. And so you can see the first one, u at 0 is equal to 0. And u at pi over 3 is the square root of 3. All we did is just take the tangent of 0 and the tangent of pi over 3. Now, when I do my substitution, and I've substituted everything in for the original integrand and these limits of integration, what I have is an integral that is numerically equivalent to the original integral. So there's no reason for me to do any back substitution like we did with the indefinite integrals. Because remember, when we take a definite integral, I'm just trying to get a numerical value as a solution. So as long as it's numerically equivalent, I can just solve the integral from here. So I took the antiderivative, I got u squared over 2, evaluated from 0 to square root of 3, and we end up with 3/2. And that's really the way that I would want for you to solve this. Now, the other thing you could do, if you wanted to, is you could change it back in terms of the original function that we had for u. U was tangent x, and I can change my limits of integration back to go from 0 to pi over 3 again, because those are x values, and I still get 3/2. But the reality is this is not necessary, right? We don't need to do that. We've already gotten 3/2 without doing the back substitution. It's just an extra step that's completely unnecessary because we changed those u values or those limits of integration into u values. All right, so I'll go through a couple of examples and then I'll have you try a couple of these, and you'll see this is actually a pretty simple process. So here I've got x over x squared minus 4 integrated from 0 to 1. So I'm going to say my u is x squared minus 4. And remember, I didn't really just jump into that. I want to think about, okay, if I choose x squared minus 4, is my du going to make sense here? And in this case, I know that it does. So du would be 2x dx. And that means I need a 2 here and a 1/2 on the outside so I can do my substitution. Now, when I do this substitution, that 1/2 still there, but now I'm going to have du over u. And my limits of integration, what was a lower limit of 0, well, if I plug it into my u expression, 0 squared minus 4 gives me -4. And the upper limit of 1 gives me 1 minus 4, which is -3. And now I've got an integral that is numerically equivalent to the original integral. Now, you've got to be careful on this one, because notice that I've got essentially 1 over u du. I'm going to get a natural log out of this. And we've got to account for the fact that we've got those negative u values. So in this case, having the absolute value in your expression is very, very important so that we can evaluate the solution. So I am evaluating this from -4 to -3, and then I just plug that in. So I'm going to get 1/2 of natural log of 3 minus natural log of 4. Or I can write that as 1/2 natural log of 3/4. Or I can have natural log of 3/4 to the 1/2. I can write this one in a lot of different ways. But the main thing is you can see the u substitution and you can see how I changed the limits of integration. So it's not really that difficult to do. The place where people tend to make a mistake on this is they forget to change their limits of integration. So remember, the original limits of integration are x values. We have to convert them so that they match up with whatever we're substituting. Typically, we're going to use u for substitution. So we want to convert them to u values. Okay, so let me just go through one more of these. Here we've got x e to the x squared dx evaluated from 0 to 2. It's pretty obvious this time that I'm going to do my u to be x squared. My du would be 2x dx. So I can tell to do my substitution, I'm going to need a 2 here, which means I need to put a 1/2 on the outside so I don't change the value of the function. And now I'm just going to go through my substitution. So e to the x squared becomes e to the u. 2x dx becomes du. And now my limits of integration, 0 squared is just 0, and 2 squared is 4. So again, now I have an integral that is numerically equivalent to the one I started with. So now just go through and take your antiderivative. This would be 1/2. I'm going to get e to the u evaluated from 0 to 4. And in the end, I've got 1/2 of e to the 4th power minus e to the 0 power. Or I could write that as 1/2 times e to the 4th minus 1. Or I could have e to the 4th minus 1 all over 2. So you can write it in different ways again, but the main thing is the substitution part of this. All right, so there are 2 more questions there, and you've got 2 more on the next page. So what I want you to do is pause the video and work through those next 4 questions, and when you unpause it, I will show you the solutions. Okay, so here's the last 2. You can see that we had tangent cubed over cosine squared. So it wasn't obvious right away, but we can rewrite this as tangent cubed times secant squared, and then you can see the u would be tangent, the du would be secant squared, and the main thing is don't forget to change those limits of integration. And once you change the limits, now I've got a really, really simple integral. U cubed evaluated from 0 to 1, and remember that's numerically equivalent to what I started with. So I started with something that looked really messy, and now I've got it into something that's just basic power rule, and you can see that would be 1/4. This one, we've got dt over 5 minus t. You can see that I chose my u to be 5 minus t. My du is negative dt. So I needed a negative in the integral, so I put a negative outside again to make sure that I don't change the value of the integral. And now, when I do my substitution, I've got the negative of the integral from 4 to 2 of du over u. I could have solved it that way and it would have been totally fine. But for me, I usually will go through and switch the limits of integration when they're not in the correct order like they are here. So I went ahead and switched them and made it the integral from 2 to 4. If you didn't do it that way, that's fine. You're still going to get the same answer. It's just that your algebra to get there will be slightly different. But in the end, you're going to get the natural log of 2 for this one. So again, fairly simple. Okay, so here we had e to the negative cosine theta, sine theta, d theta. You can see that this substitution, actually, everything's already here that we need. So my u is negative cosine theta, my du is sine theta, d theta. And again, don't forget to change those limits of integration. Negative cosine of 0 is negative 1, and negative cosine of pi over 2 is 0. So then get your antiderivative, plug in your upper limit minus your lower limit. Either one of these answers would be okay, but you would probably see it written as e to the 1st power, or excuse me, e minus 1 over e. And then the last one here, we've got x over 3 plus x to the 4th. Now this one's a little bit more difficult because we have to recognize that we're actually going to end up using an inverse tangent here, and you might not see this right away. But what I did was I factored out a 1/3. So when I looked at this, I recognized that this looks a little bit like an inverse tangent. So knowing that it looked a little like an inverse tangent, I factored the 3 out of the denominator so that I'd have a 1 plus something squared. And in this case, I've got x squared over the square root of 3 squared. So you can see my substitution here that I did. I made my u x squared over square root of 3. That means my du is 2x over root 3. So I've got to do a little bit of work to make that 2x over root 3 show up here. But since I have an x in the numerator, I can multiply it by 2 over root 3. That just means on the outside of the integral, I have to multiply by root 3 over 2. And once I've sort of set this up for the substitution, I didn't do the substitution yet right here. I just set it up to make it really obvious what the substitution is going to be. So now I can change that integrand into 1 over 1 plus u squared du. And my limits of integration, remember, we've got to plug in here. Any u value is going to be the x value squared divided by the square root of 3. So I ended up with limits of integration of 1 over square root of 3 and 2 over square root of 3. And then from there, it's an inverse tangent, plugged in my values, and you can see my solutions here, or my solution was root 3 over 6 times inverse tangent of 2 over root 3 minus inverse tangent of 1 over root 3. And we might be able to use some unit circle values to simplify that down a little bit, but the main idea was the substitution and remembering to change those limits of integration. Okay, so the last thing that I have for you here in this unit is what's in this last section. So really what this is primarily focused on the idea of a function defined by an integral. And there's a little bit of problem solving involved in this section, but we talked about this before, so I don't really want to spend a ton of time on this, but just as a reminder, so this will be in problem solving scenarios, but when we have a derivative and we want to write a function that is the antiderivative function of that, and we can't take the antiderivative, what we're going to do is just write the function in terms of an integral. So this one we have dy dx is cosine x cubed, and we know that when when x is 1, y has to be 4. So all I'm going to do here is just rewrite my solution here as y is equal to, and remember we're going to do the integral from something to x. We're going to write our function in terms of t. We're going to use that dummy variable as a placeholder. And now we need to force it to go through the point 1, 4. So I'm going to choose my lower limit to be 1 so that when I plug 1 into this function, the integral becomes 0, and then I just can add 4 to that. Okay, so that's the main idea that you'll need in that section. Keep in mind, you'll be using that in problem-solving situations, but it's still the overall main idea is going to be the same.